Alpha-haloketones rearrange in the presence of a base and a nucleophile to yield carboxylic acid or an ester. The reaction is known as Favorskii rearrangement, which can occur both in acyclic ketones as well as in cyclic ketones. In this video, we'll talk about the mechanism for both acyclic and cyclic ketones accordingly. So let's begin. Right, so Favorskii rearrangement involves the skeletal rearrangement of alpha haloketones that contains at least one alpha hydrogen to the corresponding carboxylic acids, esters, or amides in the presence of an appropriate nucleophile and a base. The primary requirement for this reaction to happen is the presence of at least one alpha hydrogen on this side, on the opposite side of the ketone, the side opposite to which the halogen is attached. So let's see how the mechanism works. But before that, let me tell you that the reaction proceeds via a cyclopropanone intermediate. So let's see how it proceeds. So here is our ketone. In fact, the alpha haloketone, which contains at least one alpha hydrogen on the side opposite to which the halogen is attached. Remember, this halogen could be chlorine, bromine, or iodine. So any of these halogens can be present in the starting material, and this alpha haloketone is reacted with a base. So this base will obviously abstract the acidic alpha hydrogen, leading to the formation of an enolate anion. This enolate anion will collapse, and as a result, these pi electrons will attack the alpha carbon on the other side of the ketone, allowing the removal of the halide anion. And you can see that we have the formation of this cyclopropanone intermediate with alkyl groups on both sides of the ketone. Now, in the second step, an appropriate nucleophile is allowed to react with this cyclopropanone. Now, you can use different types of nucleophiles, for example, water, alcohol, or even amines can be used as nucleophiles. So you know the characteristics of this nucleophile, which will attack this electrophilic carbonyl carbon, shifting these pi electrons towards oxygen, forming an oxyanion. This oxyanion will collapse back, and now at this stage it will lead to the cleavage of one of these two bonds. Either this bond or this carbon-carbon bond is broken, right? So it leads to the cleavage of, for example, this bond. It forms a carbanion on this carbon. With the formation of the carbonyl here, which has the nucleophile attached to it, whatever nucleophile you have used, that will be attached here. And then we have this CHR group here, which is then attached to the carbanion, and it has the R group attached here. Right, so this carbanion will then abstract a proton from the solution and that will lead to the formation of a stable molecule, which would either be a carboxylic acid, an amide, or an ester. If you use water as the nucleophile, you will get carboxylic acid at the end. If you use alcohols, you will get ester at the end. And if you use amines as the nucleophile, then you will get amides at the end. So you can have OH attached here, or you can have OR attached here, or you can have NHR attached here. So this is a very interesting method to prepare highly branched carboxylic acids as well. Now, this was for the acyclic ketones, but as I told you earlier, this reaction can also take place in cyclic alpha-haloketones, as you can see the reaction here at the top, and we'll discuss the mechanism in a short while. So here is our the cyclic alpha-haloketone. This will be treated with a base, and on this side of the ketone, if we have an alpha hydrogen, that will be abstracted, forming an enolate anion, which will collapse back, making these pi electrons react at this carbon, leaving the halide anion and forming this bicyclic system with one of the rings as cyclopropanone. At this stage, the nucleophile reacts. So again, you can use water, alcohol, or amines as the nucleophile, which will attack the carbon, forming this oxyanion, which will collapse back in this form, breaking one of the carbon-carbon bonds, forming a carbanion, and on the other carbon, we will have restoration of the carbonyl group. This carbanion will then abstract a proton from the solution to form this stable molecule. Right, so you can see, you can compare the starting material, the cyclic ketone, and the product that you can see here, that ring contraction takes place during this rearrangement process. And this ring contraction is by one carbon only. So we started with a 6-membered ring, and now we have a 5-membered ring. So one of this carbon, which you can see here, comes out of the ring to form a ring with one carbon less than the starting material. Now, the reactions that we just saw, both in acyclic and cyclic ketone systems, they had symmetrical alkyl groups on both sides after the removal of the halogen. Or you can say that this cyclopropanone ring in both the cases was symmetrical. If you have a situation in which this cyclopropanone ring is asymmetric, like it has different alkyl groups attached on both sides of the carbonyl, then you cannot cleave both the carbon-carbon bonds at your will, but the bond that leads to the formation of a relatively more stabilized carbanion will be cleaved to form that particular carbanion. In this case, when we have this symmetrical cyclopropanone ring, both these carbon-carbon bonds can cleave, or there is equal chance for the cleavage of both the carbon-carbon bonds. But when there is asymmetry, then only that bond will be broken, which leads to the formation of a relatively more stabilized carbanion. So this was all about Favorskii rearrangement. Stay tuned for more named organic reactions in the upcoming videos. Thank you so much for now.